All right, so welcome to lecture 15 of natural language processing. So today we will wrap up our discussion on large language models, which we started in the last lecture. In particular, we will be discussing safety and trust with respect to large language models, or safety and trust with respect to AI in general. So today, as I said, we will be wrapping up our discussion on large language models, and we will then start with transformers. We will basically be introducing the transformer, its architecture, and its basic functions, which will then, of course, continue in the next lecture as well. So that is the agenda for today. Okay. Okay, so let's get started. All right. So we were discussing large language models in our last lecture, and large language models are actually computational agents. Uh, that have quite a large amount of capabilities, a lot of capabilities. Of course, originally they are language models, which basically means that given a context, they will give a distribution over the predicted word. So that predicted word is usually the next word if the context is the preceding set of words, or it might be a central word if the context involves both the before and after words. So these are two different types of language model. So far, we have talked about the autoregressive model, in which case the context is the preceding word and we are predicting the next word. So later on in this course, we will discuss the masked language model as well, in which we are predicting the central word given the words that appear around it. So large language models provide a distribution over the predicted word. But as I said, they are computational agents. In general, they are quite powerful and they're computational agents, and you can interact with them in natural language, and they will be able to respond to you in natural language as well. So this has made, oops, okay. So as I said, they are computational agents, not just language models. And computational agents, you can interact with them in a natural way. They understand your problem and they can respond accordingly. And this is because they have learned a lot of things from the language that they have been trained on. They can learn things about the world, things about syntax of the language, semantics of the language. They also understand discourse, meaning that some dialogue that is going on, they will be able to remember that and use that as a context for uh, responding to you. So in other words, you can think of them as chatbots, and they can, as such, solve many problems which were previously solved by other techniques. So nowadays, you can pretty much solve any NLP task using a large language model. So for example, classification can be solved through large language model. You just give uh, a, a context saying that this is a sentence or this is a review. Tell me whether this is a positive review or negative review. And Based on that context, the large language model will reason and give you an output. So as such, it can do classification. It can do, of course, this is simple text classification. It can also do token level classification. So we will see some of these examples later on. For example, POS tagging is token level classification. NER is token level classification. So it can do that as well. So you can give a sentence to a large language model and ask it to label each word in the sequence as either noun, verb, adverb, adjective, and so on. And it will be able to do that. And of course, the use of a large language model is up to your imagination. You can actually prompt it to do anything, and based on its understanding of the language and the world, it will give you an answer. Okay? Of course, it is naturally suited for tasks like summarization, okay? Tasks like machine translation, translate for transcription, for example. So it is naturally suited for these tasks because these tasks are by nature generative tasks. And a large language model is a generative engine, or you can call it a generative AI tool that generates natural language given a context. Okay? So, so we talked about evaluation of large language models last time. So, and we continued from our discussion on n-gram language modeling evaluation. So we have an extrinsic evaluation where you evaluate the performance of the large language model on tasks that you are trying to solve. So those tasks could be any of those that I mentioned above or any others. And nowadays, as you know, large language models are being produced left and right by different companies. So how do you evaluate them? You usually have a benchmark of all of these tasks, and you run those large language models on those benchmark and evaluate their performances. So the benchmark could be on summarization, benchmark could be on uh, class translation, it could be on classification, and so on. So this is extrinsic evaluation. And last time we also talked about intrinsic evaluation. So this is evaluating a large language model or language model in general on the task that is meant to do, which is to predict the next word. And the measure that we talked about was perplexity. You had a question on perplexity in the quiz as well today. Okay, so perplexity is directly based on probability and which is the core function of a language model. Of course, perplexity is normalized because when you're testing on different sizes of text, you want to be able to compare across those sizes, so you normalize that. So perplexity is normalized. But nowadays, there are other ways of quantifying large language models, other evaluation. So one, for example, is uh, the cost of training, for example. Okay? So the cost of training would include the cost of the hardware as well as the cost of running the training algorithm, which is usually electricity, energy. Okay? So that's often quite large. Okay? So the cost is a major issue. And of course, this is for training. Then, of course, the cost of use as well. The cost of use, if you're using a subscription, what is the cost of using a large language model? And if it is something that you have off the shelf, what hardware, what GPUs do you need to run that language model locally? Okay? So that's also something that you need to evaluate. You can use to evaluate a large language model. Okay? Uh, and then there are other various aspects which you can call them as extrinsic evaluation, but these are more specific to issues that arise in large language models. So for example, so fairness evaluation. How fair is your large language model? Is it biased or not biased? Or uh, did someone speak? All right. Okay. And then, of course, uh, so fairness, well, of course, these can be as many as there is a need for it. So fairness, so bias, for example, evaluation on bias. So, for example, evaluating with respect to various safety aspects of large language models. So, whenever a new language model comes out, you will see evaluations on all of these parameters. You will see extrinsic evaluation, meaning that how well it does on classification, on summarization, on translation. You will also see evaluation that tells you about its perplexity on some test set. And of course, the domain of the test set. The domain is medical, legal, and whatever. And then, of course, other measures like how much it was the cost to train this model, how is the cost of using this model, how big is the model. Uh, of course, how big is the model usually determined by the number of parameters that need to be trained. And we'll see shortly how many parameters they typically have. And then other issues like safety and uh, harm that is associated with large language models. Okay. So let me show you. So this page on Wikipedia on large language models, I think it's a good summary. You can read the chapter in the textbook as well, chapter 7, but you can also go through this page, which is well structured, and it will give you a good summary of what are the current trends in large language models today. So we'll go down. So we already talked about evaluation. So limitation and challenges, of course, we have already mentioned some of them. So hallucination is an issue that arises in large language models. So what is hallucination? So actually, we also have a slide on this. So hallucination basically refers to generated text that seems to be grammatically correct and even factually correct, but it is not factually correct. Uh, and why does this happen? Because large language models usually generate text based on probability distribution. And as such, it can use those distribution to generate text that seems plausible, that seems correct, but actually it is not, because probabilistically, uh, in the context in which that text has been generated, it might be a very reasonable text, but actually it is not. So factual correctness is one way of identifying whether a large language model's output is hallucinated or not. So nowadays, of course, there are data sets out there by which you can determine whether a given uh, or evaluate how much a given large language model hallucinates or not. So people are more or less focusing on this quite a bit in recent times to determine the hallucination uh, degree of a large language model and how to mitigate it. You can, of course, there are other frameworks as well. For example, RAG, retrieval augmented generation, is a good way of ensuring that hallucination becomes smaller, or you can fine tune your model on your local data set. So there are other ways, simpler ways of handling hallucination. But hallucination is a problem, and this problem is primarily because large language models generate text based on probability distribution, and it can generate text that is seemingly correct, but it is not. Okay. Uh, so privacy is another issue that arises in the use of large language models, and privacy has various dimensions. One dimension is, of course, since it has used a lot of data that is available out there for its training, from that large amount of data, there might be private information which you can then elicit or extract by chatting with that large language model. So maybe the large language model has been trained on company internal data, or it has been trained on medical records, and then through by chatting through it, you can maybe trick or even directly ask the large language model to tell you about a particular person or tell you of a particular scenario which was not meant to be public. So that is privacy in one way of looking at it. Another way of looking at it is people often interact with large language models without realizing that the information is being stored or being sent over the net to a server. So they often get associated with their large language model and their interaction with it in an emotional way, and they kind of reveal their private details to the AI agent, the computational agent. So in this way also, uh, there's an issue of privacy because you are kind of voluntarily leaking your private information to the system. So privacy, as I said, is an issue, and people are working on this as well. So again, this is an active area of research. So abuse and toxicity and other stereotyping, this is an issue that has been seen right from the beginning of language models. Because when you train your language model on a specific set of data, that language model would then parrot that data or mimic that data as much as possible. If your data is biased in some way or it has stereotypes in it, so those stereotypes would be propagated in the text that is generated by the large language model. Okay? So, so this can appear in various ways or various fashions. Of course, one fashion is toxicity, because when large language models are trained on web and social media content, such content contain a lot of abuse, offensive language, and so on. So your large language model tends to learn that. So in fact, one of the early large language models made by Microsoft was taken offline, I think, within hours of its deployment, because they found out that as people interacted with it, it very quickly moved into harmful speech because it was trained on that, or a large amount of training data contained harmful speech or offensive speech. So that was, I think, in the 2015, 2016 time frame. So nowadays, of course, this is mitigated in multiple ways by ensuring that the data set does not contain such information, and then through uh, what is called as preference alignment, which we'll talk about later on as well in this course. So kind of tuning your output of your large language model, preference alignment. Uh, okay, what is the next slide? Okay, I think let's go back here. So of course, this is just about toxicity. It can be about other things as well. So there could be gender biases, there could be racial biases, ethnic biases, cultural biases. So one common bias is most of the language that goes into a large language model is English. And English has its own culture, or you can say socio-economic setup that is depicted in that language. So such large language models thus do not work very well for other languages like Urdu or other low resource languages like Pashto or Balochi and so on. And it may not reflect the cultures of such people who speak those languages. Because so that's another issue that typically arises. And of course, we need to ensure the large language model does not generate obscene information, right? So, so that's something that's protected by legal frameworks worldwide. Also, things like about how to make a bomb, for example, and things like that. So all of these things can happen by use of a large language model. There's also the issue of copyrighted information. So much of what is trained used for training a large language model may be copyrighted. For example, books and articles and so on. So a large language model would learn that explicitly, and you can prompt it to maybe return a complete passage from a book that might be copyrighted. So there are various issues associated with large language models, and all of these are active areas of research. And we are also in this our lab working on some of these problems as well. So, and of course, our focus usually is on low resource languages, languages that are relevant to our context, like Urdu. Um, okay. So we have already talked about emotional dependence before. So people tend to get emotionally attached with their system. And they also tend to ask the AI mission critical things, maybe very critical things regarding their health or mission critical things regarding life and death of other people, so that you might get correct or you might not get correct information. So that's something that you need to be aware of. And then, of course, there's the whole philosophical issue. So we have created a Frankenstein in some way. So uh, a generative AI system, an AI agent that has powers that are often better than humans in some domains. Of course, in other domains, slightly humans are still better, but their capabilities are improving. So what would happen with this system in the future? So that's an open area of debate and conjecture. People are discussing this. So how would this evolve? How would it take up jobs, for example, in the future? And how would this interact with humanity in the future, and so on? All of this you can always look up up some of the interesting debate on YouTube and other places. So, but most of this is also philosophical. It goes back to philosophy because kind of ultimately leads to the notion of existence and not existence. Okay. So, so that was, I think, the end of large language models. So, any questions or comments? Okay. So usually we do preference alignment. So we give it examples about people asking specifically about a thing that it should not ask, it should not reveal. So you will give prompts like, tell me how to make a bump. And then in the response, you say that this is something that you should not do, and you should respond by saying that this is something that I'm not allowed to tell. So ये preference alignment का एक आपको post training करनी पड़ती है. So there is a pre training that is done on all the data that you have, and there are two types of post training. Actually, one only post training, which is preference alignment, and the other training was instruction tuning. हाँ ठीक है, दोनों टाइप्स को आप पोस्ट ट्रेनिंग कह सकते हैं. सो देयर इज प्री ट्रेनिंग और पोस्ट ट्रेनिंग में इंस्ट्रक्शन ट्यूनिंग या प्रेफरेंस अलाइनमेंट है. सो यूजली दिस काइंड ऑफ थिंग्स आर हैंडल थ्रू प्रेफरेंस अलाइनमेंट. आप स्पेसिफिक एग्जांपल्स देंगे उसको, और फिर बताएंगे, जब वो रिजल्ट देगा तो उसको आप फीडबैक देंगे कि ये वाला रिजल्ट नहीं देना, ये वाला देना है. ठीक है. सो इट विल टेंड टू लर्न दैट इन फ्यूचर कन्वर्जेशंस. ठीक है. एनीथिंग एल्स? ठीक है. So let's quickly look at another thing. So this again from a page from Wikipedia has a list of large language models. So you can see that this table has almost 85 rows in it. So there are 85 large language models. And of course, there is, and of all of these starting from 2017 onward when the transformers were introduced. So the vast majority of all the large language models, I would say almost all, I'm not too sure, 100% pata nahi hai, but I would say the vast majority are based on transformers. And the transformer was introduced in 2017. ठीक है. So what I want to highlight in this table is the number of parameters. So the 2017 paper has 0.21 billion parameters. Parameters are the various parameters in a neural network or the large language model that is used. And those are the free parameters that you train or adapt using the training data. So, but as you move down this list, you'll notice that the number of parameters are increased. So nowadays, usually the number of parameters are into the hundreds of billions of parameters. ठीक है GPT-5 का बाय द वे पब्लिकली इन्होंने कोई नहीं बताया कि कितने नंबर ऑफ पैरामीटर्स हैं so we don't know the number of parameters in GPT-5 for example but most other models that are 2024 2025 hundreds of billions of parameters 200 billion 300 billion 500 billion there were also 1 trillion number of parameters some time back a couple of years back or one and a half year back but that didn't become very popular. So these are massive systems. They are not small systems. They're huge computational systems. So, and to train them, you need a lot of energy. And of course, it takes a lot of time as well and money to train them. But recently, uh, Claude, so you mentioned that Claude 4 has 1.7 trillion parameters. So that might be true. Okay, so some other one, I don't remember, follow the name. So ठीक है तो so they are large language model with over 1 trillion parameters. ठीक है and you can look at this list and find the various types that are out there. ठीक है but I just wanted to mention one thing. Recently, there has been a push towards smaller models, but with equivalent or even better performance. So DeepSeek came out, I think, last year. तो उसने quite a stir create किया था कि ये स्मॉल साइज पे लो कॉस्ट पे भी उतनी परफॉर्मेंस दे रहा है GPT-4 दे रहा था ठीक है एंड रिसेंटली दे आर some architectural changes like using large language models in hierarchical fashions, for example HRM, that overall takes fewer number of parameters and does as well as larger parameter models. ठीक है so this trend I think would continue for some time in the future, uh, which we will and the performance would increase by architectural change, not just by increase in size and increase in data. According to my analysis, we have kind of reached a plateau in terms of increase in size and increase in performance. वो probably अब और ज़्यादा performance increase नहीं होगी, just based on large size and based on large number of parameters. ठीक है. So any other question or comment? All right. All right. So now let's move on to transformers. So so this is the main building block of large language models today. And this is a neural network architecture. And the main component or main strength of this architecture is what is known as the uh, attention mechanism. ठीक है? So the transformer, as you saw in the list as well, was introduced in 2017. So it's relatively new. Of course, the concept of attention in neural networks is relatively older. Uh, Concept of attention in neural network is older, I think, and goes back to early 2000s and even older if you find papers that were not well recognized earlier on. But using attention in a feed-forward type of approach was done by this guy, I think Baswami, in 2017, and he named it the transformer. Okay, so that's the architecture that we are going to look into today. So let me see. By the way, transformer is chapter 8 of your textbook. अभी लार्ज लैंग्वेज मॉडल जो हमने पिछले देखा था वो चैप्टर 7. So we already know large language models today are built out of transformers. Okay. This timeline is approximate as mentioned in the heading, and it's more based on the first use of a concept. But that concept, when it was first introduced, may not have garnered much popularity. उस वक्त लोगों को शायद नहीं पता चला था. So, for example, the idea of embeddings and static embeddings was presented or known in the early 1990s, but it only became known or popular in the early 2000s. Okay? So similarly, if I do, although that's not in this list, but जैसे जो recurrent neural networks का जो LSTM model है, which we discuss later on, long short term memory model, was proposed in 1997. ठीक है? और वो पेपर काफी सेमिनल पेपर था, बट उस वक्त इतना उसका पॉपुलैरिटी कोई नहीं हुई थी. इट बिकेम मोर पॉपुलर इन द 2000s when it was used or applied to language modeling. ठीक है? So neural language models were in the early 2000s, and mostly early then was feed-forward neural networks and recurrent neural networks, including its variations like long short-term memory models and GRU and so on. So the idea of attention was first used in 2015 in the context of recurrent neural networks. ठीक है? So 2015 में recurrent neural networks में attention propose किया गया था, but then it was moved into a kind of a feed-forward approach in 2017 to form the transformer. ठीक है? And then, of course, after that, everyone started using transformer, and the variation of the transformer was the bidirectional transformer in 2018 that led to contextual embeddings and so on. And then after that, you had the whole list of large language models, and one after the other. ठीक है? So the key idea of transformer is attention. And this is a kind of a big picture. And you will notice that some of the figures that we will draw now for neural networks would be like in block form. So you won't find those single lines from single input units that we used to do for feed-forward neural networks, because they cannot be done because it is much more complicated now. Because we often have to work with vectors or other shapes rather than just single units, handling scalars. ठीक है ना? So this is kind of a diagram showing a transformer, and input starts from below, get embeddings. Embeddings then go through multiple transformer blocks. Each transformer blocks would consist further of multiple networks, and most importantly, it will have the multi-head attention network, which is the main component of a transformer. And then after that, you have the output layer, which in this case you can think of as the language generation unit that generates a token for each input uh, after passing through all of these transformations. The idea of the attention is that, so given an input, which is a vector, which is a sequence of words, and each word represented by a embedding. Remember, each word is now also a vector. So you have a sequence of words, each word is a vector. So that vector of a word goes through processing such that it can be influenced by the other words to the right as well as to the left in general of that word. But in this chapter, we will primarily focus on autoregressive transformers in which a particular word can attend to or is influenced by all the words that precede it, including itself. ठीक है? And this is, you can think of this as डायरेक्ट लिंक्स. आपको इंडिविजुअल लिंक्स की बात करें तो ये लेट्स से एक नोड है और या एक वर्ड है, इसका वर्ड का एक लिंक इस पिछले वर्ड के साथ भी है, इसका उससे पिछले के साथ भी है, उसके पिछले. सो दे आर डायरेक्ट लिंक्स फ्रॉम दिस वर्ड टू एवरी वर्ड that has appeared before it. And this direct link can influence this word and its output. So that's the key idea of a attention mechanism, meaning that all the other words that precede it can attend to this particular word. If there is a similarity between this word and this word, then it should be reflected in it. So let's see some examples and maybe you can get a better idea of the issue of attention. So, so we have talked about lexical semantics in a few lectures back, where we discussed words and their meanings. And we then talked about static embeddings, which was word to vec, for example. So static embedding was learned on a large amount of data, and you had only just one representation for a word. So which hopefully would capture all the meanings for that word. But as you know, meanings can vary with context. So for example, let me write two sentences. Uh, they picnicked on the bank, for example, and I met the manager of the bank. So in this two sentences, we have the same word bank, and this is a polysemous word, bank. In the first context, picnicked on the bank, this bank would most likely be a river bank or some other related spot close to water. But in the second case, the bank would be if a financial institution because we are referring to a manager. So this bank का जो representation होगी, it will be influenced by all the word before it and most particularly by the word manager in the second sentence. And in the first sentence, it will be most primarily influenced by the word picnic. जब उस बैंक का वर्ड को पता चला कि पीछे पिकनिक आया हुआ है तो उसकी वो एम्बेडिंग वो चेंज कर देगा, उसकी रिप्रेजेंटेशन वो चेंज कर देगा. सिमिलरली बैंक के पहले उसको पता चला कि मैनेजर आया है तो इसका वो रिप्रेजेंटेशन चेंज कर देगा. ठीक है. वाइल इन द प्रीवियस केस जब हम वर्ड टू वर्क लर्न करें तो बैंक की एक ही एम्बेडिंग थी जिसमें होपफुली ये सारी रिप्रेजेंटेशंस थी, बट स्पेसिफिकली फॉर अ पर्टिकुलर कॉन्टेक्स्ट नहीं था. So similarly, you can think of some other examples like, for example, uh, the flights uh, to, for example, let's say Islamabad, Lahore, Karachi were. ठीक है. So were is a plural. Were is a plural. So let's say if you wanted to predict this word were, given the context that appeared before it. So the best prediction, as we know from this sentence, is the plural word, not the singular was, because flights is plural. ठीक है. If flight was singular, तो ये आगे were was होना चाहिए था. ठीक है. And this word flight could have appeared any number of words before this word were. बिकॉज बीच में और भी वर्ड्स हो सकते हैं, बेताशा और वर्ड्स होते हैं, और हमको एग्जैक्ट पता नहीं है फ्लाइट्स किधर आ रहा है पहले. सो ए ट्रांसफॉर्मर मॉडल कैन लर्न दिस बिहेवियर by attending to each of the words that appear before it, और जिसके साथ उसकी एसोसिएशन ज्यादा बन रही है उसको वो ज्यादा वेट देगा. ठीक है. तो वर्ड का जो प्रिडिक्शन है वो डिपेंड्स ऑन द कॉन्टेक्स्ट, एंड दिस पर्टिकुलर केस फ्लाइट्स के साथ ज्यादा रिलेशन है. फ्लाइट सिंगुलर होता तो ये वॉज होना था. तो एक और एग्जांपल ले लेते हैं. दिस इज आल्सो इन द स्लाइड्स. सो फॉर एग्जांपल द चिकन, चिकन के स्पेलिंग को क्या हो गया, चिकन क्रॉस द रोड, road because it was to dash dash dash. तो यहाँ कौन सा वर्ड आएगा? सो लेट्स से यहाँ मैं वाइड या टायर्ड कहता हूँ, दो पॉसिबिलिटीज हैं. अब जब मैं वाइड की बात कर रहा हूँ, दिस वाइड वुड रिलेट टू द वर्ड रोड. फिर हम, as you can see from the sentence, then this wide is referring or relating the word road, not the word chicken. But let's say मैं tired use करूंगा, तो then that tired is referring to the word chicken. So again, different attentions of a particular word based on the context. And we would like to learn this attention, and this is learning mechanism is thus provided by a transformer. ठीक है. So we did not cover recurrent neural networks before, and we might study them later on as well. Recurrent neural networks में भी previous context हम ले सकते थे, but उसमें one by one था. So let's say if you talk about the first word, bank का context पिछला word होगा दी के बाद off होगा and so on. तो जितनी बड़ी change जाती जाएगी उसका influence कम होता जाएगा. While in the case of transformer, you have direct relationship of each word with every previous word. It's not a sequential relationship. बैंक तो पहले डी की तरफ आएगा, डी को ऑफ को जाएगा, ऑफ को सो ऑन until we reach मैनेजर. इन द केस ऑफ ट्रांसफॉर्मर, बैंक डायरेक्टली एक मैनेजर के साथ भी लिंक है, बैंक बैंक का डायरेक्टर डी के साथ भी है, ऑफ के साथ भी है, सो ऑन. ठीक है. सो वी डोंट fall into that trap that was typically occurring in a recurrent neural network. ठीक है. तो अच्छा, तो इसके बाद थोड़ी सी हम नोटेशन शुरू करेंगे. मेरे ख्याल से टाइम खत्म हो रहा है. आई माइट स्टॉप हियर. सो द रेस्ट ऑफ द लेक्चर वुड बी primarily based on equations and some notations, so which will kind of solidify this intuition of attention, and then we'll follow it up with the complete transformer, so which we'll do probably in the next lecture. ठीक है. So any comments or questions? Any questions? Okay. So so we will have a lecture on Wednesday, and that will be on transformers. So, and then next Monday we have a midterm exam. So midterm exam obviously would contain everything that we have covered so far. And उसका थोड़ा बता format वगैरह मैं आपको email कर दूंगा, but it will be very similar to the one that you saw in the quizzes. And it will be 75 minutes long in class. ठीक है. 75 to maybe 80 minutes long. 2 बजे next Monday को. ठीक है।